start, right? And we will continue with normalizing flow for most of the lecture today. And then towards the end of the lecture, I will give you a brief overview of denoising diffusion model, which is perhaps the state of the art in today's time when it comes to generative modeling. And then on Monday, we will wrap up our discussion on denoising diffusion model. So that is kind of the idea. And I'm hoping to end this course on Monday so that on Thursday there is no lecture. So Monday I will try to wrap it up. Okay, so that will potentially be the last lecture in this course. So major will be on the exact date and it will be written. If you want reference for question, it is like homework. The derivations that you see in homework. So that is the kind of pattern you can expect. I am not planning to give any MCQ or even a part of that, but I might decide to give one or two, but mostly it will be derivation based. Okay. So I think that is on 19th, if I'm not wrong, which is Tuesday. Right. Not only that, we have to also decide the date for the final presentation of the project, and that we will discuss at the end of today's lecture. Remind me if I forget. And the potential dates are next Wednesday in practical time. That is one. The other one is after 27th, so after your majors. So 28, 29, 28 most probably. So these are the two possible dates. We'll discuss it at the end of today's lecture. Okay, so these are the two potential dates that I am looking at for the presentation, the term project presentation, right? And for major, I repeat, the syllabus is up to Gaussian process GPLVM. So what I did last lecture is not included, what we will do today is not included, what we will do next time is not included in your major syllabus. Obviously in the homework these portions are there, at least some of these are there, so that is the idea. Because anyways I cannot give any, it is very difficult to give question from here. Neural network, it's generally coding based mostly, so little bit difficult to ask questions. Okay. So with that, let us continue with our discussion on normalizing flow that we started last time. So let us first have a quick recap because there were new concepts or old concepts we revisited after a long time. So the first thing in normalizing flow that we discussed was that it's a generative model. So what we are looking at is we want to generate X as or from Z, where Z is potentially some low dimensional known distribution, for example Gaussian. X is your target distribution, so you have data of X, you want to learn the distribution, so X is the sample and it is the distribution of X that you are interested in, right? And this is not the idea of, this idea is not specific to normalizing flow, this is for any generative model. As we said, probabilistic PCA, factor analysis, all of those are having or following this idea. Yeah, the form of f theta changes, but the idea remains more or less like this, that you have a low dimensional space, from there you want to learn the distribution. So the idea is that because the low dimensional space Z, the distribution is known, Gaussian uniform, you can draw samples. Each sample you pass through f theta, you will get samples of X. So it's like an implicit distribution that you are trying to learn. You will not have a form of the distribution, but you can generate samples of the distribution. Correct? So this is where we started. And then another important aspect that we discussed was that in normalizing flow, we use the transformation of distribution, which is for X, let's say fxx is equal to fzz, and then I am considering multivariate case. So for multivariate case, it is determinant of the Jacobian del z del x. right? And this is exact, this transformation is exact if you know the exact relays exact f theta. If f theta is exact, this transformation is exact. But in most cases, f theta will not be exact. If theta is having a theta, because that is supposed to be some form of neural network which is to be learned, and if f theta is not exact, this will not be exact. So because this will potentially not be exact, what you do is that we generally write it as f x is approximately equal to q theta x. So q theta is my approximate distribution, and it is parameterized by theta, the same theta you saw above, which are the parameters that you want to train or learn, and that is equal to f z. Now z, if x is equal to f theta z, then z is equal to f theta inverse x. So f z z, here you will get f theta inverse x, and then determinant of del f theta inverse x del x. Okay. Where theta, wherever you see theta, those are the unknowns. Theta you don't know, and you have to train it. And so, and how do you train theta? You will want your q theta to be as close as possible to fxx. So that approximation sign you see there, that has to be as close as possible. You will want, ideally you will want it to be equal, right? And if it is equal, then or the theta that minimizes the discrepancy is your theta, right? And these are things we have discussed last time, but this expression I wrote at the end gives us an important factor or important observation is there, is that not any f theta we can use, we have to use a f theta that is invertible. So we need a invertible f theta, and that's why the name is invertible neural network. We want f theta to be invertible, and we want this determinant to be easily computable. You should be able to compute it easily, right? And for that we discussed, or we introduced in the last lecture, the affine coupling layer. So in the last lecture we have already introduced affine coupling layer, right? And what is the form or the equation for affine coupling layer? It is x1 dash is equal to x1, x2 dash is equal to exponential of scale, I will write theta here, x1 Hadamard product, which means element wise multiplication, x2 plus t of theta x1, t of theta x1, right? So that is the affine coupling layer that we discussed last time. And what is the characteristic of this layer? The characteristic is that it is by default invertible, right? Because you can write x1 is equal to x1 dash and x2 is equal to x2 dash minus t theta x1 dash multiplied by exponential of minus s theta x1 dash. So this is invertible, okay? And that is what we need, because we want f theta to be invertible at the top, right? And not only that, if you calculate the Jacobian of this, you will realize the Jacobian will come out to be a lower triangular matrix. And because it is lower triangular matrix, the determinant will be product of the diagonals. And product of the diagonals, that means it is easy to compute. So that was the second requirement. Both the requirements are satisfied. Correct? So that is what this affine coupling layer allows us to do, right? And these are things we have discussed last time, we have introduced last time. One more thing we introduced last time is the loss function, okay, or how do you train it? And we introduce a loss function L theta. And what is the loss function that we introduced? Can you remind me? What was the loss function? KL divergence between f of x and q theta of x. Why this sequence? No, why not q theta and f? Why not the reverse? That's sample. We'll use the sample, right? Right. So this with this KL divergence between fxx and q theta x, right? So this is what we introduced last time, and the idea here is that we are using the forward KL divergence because we have samples of x. We will use those samples to compute the mean, because this is going to give me what? This is basically is equal to integration of fxx log of fxx q theta x dx, right? This is what it is going to give me, and this is equal to minus integration fxx log of q theta x dx plus constant, because fxx is not a function of theta, so that term is like a constant in theta, what I mean by that, right? So and what is this term? This is equal to negative of the expectation, negative expectation with respect to fx, so f log of q theta x. And this is something we introduced in our last lecture itself, that this is going to be our loss function. So we want to minimize it or maximize the, if we remove the negative sign, then we want to maximize it. We want to maximize the data likelihood or minimize the negative of that, right? And these are things we have introduced, right? So now, with all these ingredients, we now let us try to look into the implementation point of view, that if I give you some data, how are you going to implement this? Because these are like ingredients here and there. We know that all of these are going to be used, but how? And for that, some concept of neural network is needed, and that we discussed yesterday in the practical, and that is enough, the amount of neural network we discussed yesterday, right? Okay, so now coming to the implementation. So this is new stuff that we are starting today. Obviously, splitting and all those things we have discussed, that I am not reviewing again, that if you have a single vector, you can split it and all those things, so that I am not discussing now. But obviously, that will be needed. Okay. So coming to implementation, right? So this is a generative model, unsupervised learning algorithm. So to start with, what will be available to you? Data in form of what? What will be available? What kind of data will be available in unsupervised learning? Unlabeled data. It will be like only X. So your data will be xi, I equal to 1 to n. Okay. How will each xi look like? What is this each xi? Each xi corresponds to what? Vector, or it can be matrix also, images. So this is xi, one data point is like a time series, is like an image. So either vector or matrix, that's what we are talking about. Let's talk about vector. It's not a scalar, remember. If it is a scalar, you will not be able to use invertible as it is. Can someone tell me why we cannot use invertible if xi is a scalar? What will be the problem if xi is a scalar if in using invertible neural network or normalizing flow? Correct. So even if you split, when you are splitting, we need x1 and x2. So even if we have a single thing, we will split it into x1 and x2, or we'll transform a linear projection and then split it into x1 and x2. But at the very least, we need x1 and x2. So the minimum dimensions would be 2. At least the way it is. Later we will discuss how we can do it for one dimension, but that will come in a little while. Okay. So for now, xi, remember the dimension is minimum 2. Because otherwise this affine coupling layer you cannot use. Clear? So xi is a vector of dimension d, where d is greater than or equal to 2. Okay, at least. So this is what is given to you. Okay, what is the objective? Generate new x, right? Unsupervised learning, generative model. I want to generate new x from the same distribution of x, which is unknown to us, right? So for that, we will define a neural network where each layer is a affine coupling layer. So for this, I will define a neural network which is of the form x is equal to f theta z, as we have been doing. But how will this f theta look like? Let us now have a look. So we will start with z. From there I have h1, h2, hn, and then I am generating x. Okay. So we start from z, which is a known distribution. We will assume it to be Gaussian. So we know that this is Gaussian 0, I. Okay. This is training data or data that is available to us, data or the variable or whatever. But this is basically what we are interested in, what we are measuring and what we want to generate. So x is basically what you are measuring, what you are interested in and what you want to generate, correct? And then this z to h1, h1 to h2, what is those? Each of those arrows? Each of those arrows are affine coupling block. Okay. So this, all of these are affine coupling layer. Okay. And each of this layer will have S and T, right? S is the scale and T is the translation. And this scale and translation are networks. So they are neural network, like we discussed yesterday. And each layer will have its own scale and translational or translation network. So each layer, affine coupling layer, will have its own scaling network and own translating or translational network, right? So that means each one of this you are seeing will have its own theta, or we'll call it theta 1, theta 2, something like that, and combiningly we'll call them theta. Clear? So that's why if I go back, you will see here that I was writing S theta and T theta, which means S and T are neural networks parameterized by theta. And this includes all the theta, but in reality, in a layer, it will be subset of those. Let's say theta 1. Okay, theta 1 itself will be a vector, but let's say theta 1. This part is clear? Clear? Okay. So now you have here Okay, there is one mistake here. Not a mistake, but I will call it NS. Okay, because I've used HN, so that should not match. Okay, so that's why, to be consistent. So I have N or N plus 1 layers, right? Starting from X, Z, I go to X in N plus 1 steps, something like that, right? And each of those steps are affine coupling layer. I have already told you that each of these affine coupling layer will have its own scaling network and translation network. So they will have their own theta that you have to train. But not only that, if you are using the splitting scheme that we discussed last time, then it should be random splitting and the splitting should be different. Randomly, if it is random, it will automatically be different, but it should be randomly split in each of these. You should not use the same splitting throughout. Okay, that we discussed last time. And not only that, alternative of splitting is using random linear projection. If you use random linear projection from last time, then what should change? Then the splitting can remain same, but the projection matrix S should change in each layer. Each layer should have its own projection matrix. And why is it needed? Because if you don't do it, then one portion of your image or signal or your input will remain as it is. That will not be transformed, because x1 is equal to x1 dash. If x1 portion remains same, then throughout it will remain same. So you will not be able to learn anything, right? So that is why each of these affine coupling layer will have its own scaling, own translation and own splitting. All of this. Clear? So okay, let me write it down. So each affine coupling layer will have its own S theta, T theta, and S, which is the projection matrix, linear projection matrix. Clear? And each of these S theta and theta will have its own hyperparameters, number of layers, number of activation function, and all of those things you have to tune based on validation data set. So remember, so there are multiple networks that are sitting within each affine coupling, which is within a network. Clear? Now to repeat what I told at the beginning of the last lecture, this is called normalizing flow, because you are flowing from Z to X through different layers. You can think of the distribution changing slowly and flowing through each layer, and that's the normalizing flow. That's how the name comes. In fact, that's why it's called flow. It's called normalizing because you can flow in the opposite direction. You can also flow from X to Z. So you can normalize. So that's how the name normalizing comes, right? Anyways, what we have discussed till now is the forward pass. But in invertible, there is also backward pass. So let us discuss the backward pass next. So backward pass is what? Z is equal to f theta inverse x, right? And we know by now that this is now trivial, given that we are using affine coupling layer. Affine coupling layer by design is invertible, so this is a trivial thing. For a generic network, this is not trivial. In fact, this is not guaranteed. In most cases, you will not be able to invert it for a generalized network. So it is the affine coupling transformation that we discussed that allows it to be invertible. Okay. And how does it look? It looks like Z to Hn. Okay. So you have Z, but now the flow is in the opposite direction. H1, H2, Hn, X. Right? So backward pass, the arrow just changes. and that's why f theta inverse. So each affine coupling layer you will use the backward pass formula instead of the forward pass formula, right? So now with that background, we have two paths, forward and backward. So can you tell me which path will be used? When will we be going forward and when will we be going backward? Any idea? Any guess? Any intuition? When the forward pass will be used and when the backward pass will be used? Any intuition? Remember, it is a generative model. So that is one clue. Repeat, forward. Forward when we are generating data. So that is during inference. And backward, training. So forward is obvious because it's a generative model. I will sample Z and generate X. Backward, he said, and that's correct, that it is during training. Why during training? Look at the formula. Remember the formula? You have Q theta. Q theta is what? That formula. And you see inside that f theta inverse is sitting. So during training, this Q, you will work with this loss function. And if you are working with this loss function, then you have to use this Q theta. And if you are using this Q theta, then f theta inverse is sitting, which means you will use the backward pass. So during training, you use the backward pass. During inference, you use the forward pass. Clear? So we use f theta during inference and f theta inverse during training. Okay. Now there is one more challenge here. Because I am not using a single layer will never work, right? So I am using multiple of these affine coupling layers. Calculation of del Z by del, calculation of the Jacobian is to be checked whether that is still trivial or that has become difficult or not, right? So what will be the Jacobian? So Jacobian is del Z del X, right? So how will you compute this Jacobian? Can you tell me? Okay, first of all, whether you will calculate the Jacobian from the forward pass or the backward pass? Backward, right? So now how will you compute del Z by del X? It's the Markovian kind of thing you were saying, that X is influencing Hn is Hn minus 1 in the backward. So you will use the chain rule, right? And chain rule, what does it gives you? The chain rule will give you del Z, del H1, del H1, del H2, del Hn, del X, right? So that's the chain rule of differentiation that we are using. Clear? And now each of these derivative that you see, each of the Jacobian that you are seeing here is Jacobian of the affine coupling layer. And what is the Jacobian of the affine coupling layer? How does it look like? Can someone remind me from last time? Block matrix, first of all. Jacobian will become a block matrix. Identity at top left, diagonal at bottom right, but with exponential of s, that term. Others does not matter because I am going to take the determinant, so that will not matter. So it will become a lower triangular matrix. but what we will care about is basically the diagonal, and the diagonal will be I at the top left, bottom right will be exponential of s I or j, and then it will be seen diagonally, right? And we saw it last time, we derived it last time, right? So it will be like that. So each of this is now known to you. Each of the Jacobian from our discussion in the last lecture is already known to you. So all you have to do is do a product of the Jacobian, correct? But actually that is also not needed, because we don't care about the Jacobian, we care about the absolute of the determinant of the Jacobian, right? So what will be absolute of the determinant of the Jacobian? So therefore, absolute determinant x is equal to determinant, okay, this I will write in a, okay, I will write it later. For now, let us write like this: del z, del h1, del h1, del h2, del hn, del x, right? Clear? Okay, so what I wanted to write was as a product form. So I can write it as a product form. I equal to 1 to n del h I minus 1 by del h I. Okay, it should be n plus 1. Okay, where h of n plus 1 is equal to x and h of 0 is equal to z. Okay, so that is the notation I am using. So with that you can write it like that. Okay. Okay, but anyways, so this is just a notation. Coming back to the actual thing, what is determinant of product of a matrix? Determinant of AB is equal to A multiplied by determinant of B. That means all you need is the determinant, which is anyways a very simple formula of the product of the diagonals, and then you will do product of those determinant for each layer, and that will give you the determinant of the Jacobian. So this is equal to then determinant of del h I minus 1 by del h I and this is equal to product I equal to 1 to n plus 1, right? Clear from this simple determinant, matrix determinant formula? So we have we can compute the overall determinant of the Jacobian just by calculating determinant of each of the layer and doing a product of that. Clear? Any question? If there is no question, one more thing I would like to do, the last thing is revisit the loss function once more and then look at it and see if we can simplify it. I will not be simplifying it, but I will be pointing out how you can simplify it. Okay. So what is the L theta? It was expectation with respect to f q theta of x, right? This is what my loss function was or is, correct? I think there was a negative sign that I am missing. So, okay. And what is q theta? This is equal to f z x determinant of del z del x, something like this, right? So now let us look into it and try to examine it. Okay. First of all, what is x? X is equal to f theta inverse z, We know that, right? So let us write it down. So this is equal to fz f theta inverse z determinant of del f theta inverse z del x, right here. F theta no, z is equal to f theta inverse x, right? So this is wrong. X, this should have been z. Okay, that was wrong. Okay. Okay. So now, can someone tell me what is fz? What is this? What do you know about this fz? Or what do you know about this whole expression? Because we want to simplify it. To use it, is this known or unknown? Yeah, what you will assume that, right? So that is Gaussian. This fz is known to you. It's a Gaussian distribution, right? F theta of x is known to you. So what are you doing? Think about it. X is your training sample. So take one sample. Okay. You have initialized theta, so some theta is known to you. That might not be correct, but some theta you have. So because that theta is known to you, you will pass that x through your network. It will give you some output which is supposed to be z. Correct? That output you get, you will put it into the PDF of the Gaussian. And that will give you the first term. Clear what we are doing? I'll repeat once more. The training data x is known to you. You have the training data. So you will take data, let's say one data at a time. You can take more, but let's say I take one data. So that data I have taken, I will pass it through the network. Okay. If I pass it through the network, I will potentially get z. Clear? That whatever I am getting, I will put it into the expression of Gaussian. That will give me this expression. Right? And remember that theta is actually unknown, so it will become a function of theta, at least in the training part. Clear? This portion, any doubt? No, right? Okay. Coming to the second part. Second part, is it known or unknown? The second part, determinant of this whole business, is known or unknown? We just now did it. It's at the top. It's known. Right? So basically both the parts are known and both the parts are function of theta in some way, because those derivatives will be function of theta. Okay. So you will get something of a complex function in theta. Correct? That you want to optimize. So this is Gaussian. Okay. And this is known. This obviously discussed above. Right? And if these two portions are clear to you, then q theta you understand. Right? And now you have how many q theta you have? You will get like that n number of, because you have n number of x. Right? So you will use those n number of x to find out 1 by n summation, I think ns, not n, I equal to 1 to ns q theta xi. So you will do the business of q theta that we just discussed for each of the training data and take a mean of that. Okay? And that becomes your loss function. This L theta is what you want to minimize. And the value of theta that minimizes this L theta is your theta, the training, the trained parameter. Right? So I'll repeat once more. We have used affine coupling layer. And with the affine coupling layer, we have multiple of this affine coupling layer, which is mapping from z to x. And that is here. Okay. Now, because it is affine coupling layer, we also have a backward pass, which is here. During training, we use the backward path. Now, one of the key components of the loss function is the Jacobian. That Jacobian can be found out from the chain rule. But we don't care about the Jacobian, we care about the determinant of the Jacobian. Determinant of Jacobian is equal to determinant of this right hand side, which is product of the determinant, which is here. After all of this business, you want to maximize the loss function. Loss function comes from the KL divergence, and we have discussed this last time that it is of this form, right? Now, in the loss function, one Q theta is sitting. For Q theta, we have used the transformation of distribution, which gives us this form, where the first term is Gaussian. That's our assumption. It can be uniform also if you take it to be uniform. Generally, it is Gaussian. And the second term is the determinant that we have already calculated. Clear? So, using this, you can now train your model. Okay. So, the model training will be finally theta t plus 1 is equal to theta t minus eta grad of theta L theta. This is the stochastic gradient descent or gradient descent that we discussed yesterday, right? And how will you compute this gradient? Backpropagation. So, you will implement it using TensorFlow or Python or something like that, and there you can calculate this gradient. It will basically calculate it using automatic differentiation, right? Again, that I gave you a glimpse of automatic differentiation, or we discussed slightly about automatic differentiation yesterday. Same with backpropagation, we have discussed it somewhat yesterday, right? So, with that you can find out this theta t plus 1, right? So, that's all. So, this is how the network looks, that is how the algorithm is. So, the whole business is that you have affine coupling layer, multiple of those, and you use those to build your network, and that allows it to be invertible. This also gives you an open research problem, probably not an open research problem, but an interesting research problem. That like affine coupling block, you can design your own invertible neural network. That may not use affine coupling block, but maybe something better. Who knows? A better, and what do I mean by better here? More expressive. So maybe with affine coupling block, you need n number of blocks or layers. You can design, if you can, an invertible kind of thing, which might take 2 or 3, which means the more the layers, the more the number of theta, which means more is the parameter size, the parameter space, which means more is the training time. So, if you could design something which will reduce that, that's a very good problem to solve, right? So, that's kind of a very interesting problem in my opinion, okay. So, to designing your own invertible network without using or going this route, right? Any question on what we discussed till now, or is it clear? Obviously, it will only be clear if you follow the lecture, last lecture, otherwise it will not be clear, and that I cannot clarify right now, obviously, okay. So, for anyone who is watching this online, if he sees it sometime later, for them the neural network lecture is not recorded. So, in that case, they have to go back to the deep learning lecture and go through the deep neural network lectures separately, because we did not record it yesterday. So, that is not part, right. So, okay. So, this is clear. So, one of the things that we discussed was that you can only use it if d is greater than or equal to 2. Right. So, how to use it for scalar valued x? That is a small question, right? So, let us see. So, we will answer some small question now. So, how to use it for scalar valued xi? Any idea? So, that is d equal to 1. So, any idea how you can use it? I will give you one clue, it is a hack. So, it is not really, so it is like a manipulation or hack, okay. It is not really anything mathematical as such. So can you think of a hack to use it for 1D? Zero, if you do it, then what will happen? This component will be function of that. That will be problematic. Okay. But you are in the right direction. You will add a dummy variable x2 from some known distribution. Ultimately, when you generate sample, you will get a 2D sample. Each sample, and in sampling, whenever you get 2D sample, if you have to find one sample, you just remove the other, ignore the other sample. That's how sampling works. So in sampling, suppose I want to sample x. Think about it. I want to sample x, but all I know is joint distribution of x and y. So how can I sample x? I will generate x and y from those joint distribution and only select the x. I will ignore the y. That's the marginal distribution. So marginalization in sampling is the easiest thing. If from n dimensional you want one dimensional, just generate n dimensional, and then dimension you want, you just pick those values. That's your marginal distribution. Okay. So because that is the case, yeah. What is the? To be 0. So what is the transformation? Where is the trans? Here. What will happen? If you will always get 1. So then it will become, last time we discussed, before affine coupling layer, we discussed coupling layer. And in coupling layer, what is the problem? Determinant was 1. Also, there is, what are you learning now? Because to learn your neural network, your inputs, you should have different types of theta. Okay. So S theta, you will not be able to learn theta, because all your training data is now kind of problematic, right? So yeah. So some of those can be 0, but so the idea is very simple. So you want variety, right? So the idea is that introduce a dummy variable. So you have x1 and x2 you will introduce, which is dummy. And this dummy, obviously, because you are sampling, right, you will want to take it from some simple distribution. And from there you select or generate samples equal to number of x1 samples you have, and then you operate on that. That's all. Right? Second question. What if my xi are images? And this is the most common application actually. All the invertible neural network papers you will find, you will see that they are using it on images. Generative model is mostly for images. I mean, it can be for signal, time series also. There are for signals, but mostly the common one is image, or vision is where it is mostly used, right? So how will you do it if xi is an image? Because vector you were splitting, right? How will you split a matrix, first of all? And what other changes will take place? Any idea? So xi is now a matrix, image, pixels. How will you do it? Any idea? No, that's a very bad idea. You will lose all the properties of, so it will become a very big vector. I mean, and then you will not be able to handle it. Okay, that's the example I always give when I start CNN. I will not give it now, but X is a matrix image. How will you use invertible? What changes will you make? Or is there any change even needed? So there are two things you have to worry about. One is that how will the transformation change, or will it change? Second, how will the splitting work? These are the two things. If you can address this, I think this is good. Latent space, but to start with, you have one X, right? One image. Let's say grayscale, well, not even channels. So then what will you do? You have to first make it X1 and X2. So now you have only X. or xi? How will you make it xi1 and xi2? Assuming you can use the same transformation, obviously. So it's simple, you will divide the image. So break the image, split it, and put it as channels. So you are in the correct direction actually. So if I have a 4 cross 4, right, I can always make 4 2 cross 2, and they will be like channels. Now select two channels as x1, 2 as x2. Matrix. So I have something like this, right? I can split it like this. Now this is my number 1, this is my number 2, this is my number 3, this is my number. I got 4. This is one of the easiest way. There are other ways also. Okay, but this is done. There are literature which have done it. Okay, so you have split it into 4. Now first 2 can be x1, second 2 can be x2, and again random shuffling and all these things would be there, right? Clear? How can you split it? So the image size will reduce. Next, this is done, so we can split it. So now any change in the formula, affine coupling layer, will there be any changes? A very simple change will happen. Yes, S theta and T theta will become CNN. CNN is convolutional neural network, that is for images. So S theta and T theta will now become CNN. This one, so you assume it to be 4 cross 4. Okay, I have drawn 2 cross 2, but each is like 2 cross 2 again. So 4 cross 4. Okay, what have I done? I have broken down the image into small patches. Yeah, 4 cross 4, I have made 2 cross 2. How many patches will I get? 4. So those 4 patches I have now arranged, stacked one over another. So this is the first patch, second patch, third patch, fourth patch. I just now told I broke the image. That's patch. Yes, you break the image. Okay, top left portion you are getting, that is the first patch or first split. Top right is the second split. Bottom right is the third split. Bottom left is the fourth split. Obviously, you can change the numbers, but that's okay. That's all it is. Basically, break the image into small portions. Like you are breaking the vector. When you break a vector, what are you doing? You are taking the elements into 2 vectors. When you break it into matrix, it will become double, 2D, right? So it will become double, 2 will become 4. Okay. Okay. So now, that's all actually. There is no changes other than that. You will S theta and T theta will become CNN. That is one major change. And splitting will be of this pattern. Okay. And these two are enough. You don't need any other changes. Any question? Now, the last thing on invertible or normalizing flow. What will you do if the distribution is not constant? Which means distribution is changing. It can change with time or it can change with some parameter. To put thing into perspective, remember we talked about Hamiltonian Monte Carlo? There we introduced the Boltzmann distribution. It was a function of temperature. That means in statistical mechanics, the distribution changes with temperature. So what will you do if your distribution changes with time, temperature or some parameter? How will you modify the network to address such a scenario? Think about it. What if the distribution changes? And this change can be with time, with something else, right? Okay. What will you do in that case? And by the way, this is a more common setting. Most of the time the distribution do change, they do not remain constant. Okay. So you can think of it like this. Let me give you some more examples. Suppose fluid flow, right? At different time you are getting images, the flow field. So the flow field will have some distribution. The flow field can change if you change, let's say, the viscosity or the initial condition or something like that, right? Hamiltonian I already told you, something like that. Even things can change with time also. Okay. So in that case, what will you do? So in that case, we need a separate network or a separate network. Yeah, you can say that. So this is known as conditional CINN, or conditional invertible neural network or conditional normalizing flow. Okay. So in this case, what you will need is conditional invertible neural network. Okay. Clear? And what you will do is simple. So till now what were you doing was you had Z, right? It was going into some function and you were getting X. This was the setting we were working with and this was F theta, correct? In conditional, what happens is that there is a one more variable that comes into picture and this is the conditional variable. So this variable can be your, I don't know, temperature, time, some class, something like that. Now why is this needed? Because when you are training a conditional network, although some data will correspond to, let's say, temperature is equal to 10, while some will be corresponding to temperature equal to 20, but they will be sharing information. And it is the shared information that will allow you to learn the total thing easily. Whereas if you only try to learn only for, let's say, temperature equal to 10, you might not have enough data. So this allows you to share information across parameter values and to train a network that will generalize, right? So that is the idea. In fact, conditional, so I will give you one example of conditional neural network or conditional generative model. So suppose I have, so there is a very famous data set which is known as the celebrity face data set. This is a very common data set. If you search, you will get it. Okay. So celebrity face data set, what does it have? It has, I think, the number might be wrong, but around 1 million faces of celebrity, actual celebrity, both male and female, right? And then you can always train a generative model. In our case, it is the invertible network, which will learn the distribution of this celebrity face and now start generating new celebrity faces which do not exist, but they will look like celebrity, right? But it will generate faces of both male and female. In conditional, what you can do is you can condition that, okay, male. So then that network will start generating celebrity face only of male celebrity or only male faces that look like celebrity, because those are not actual celebrity. Whereas if you condition on female, it will then start generating faces of female like, say, or sorry, not female like, celebrity like female faces. Okay, right? So that is one example that people have done. If you do a Google search, you will find it. In fact, that was first done for GAN, if I am not wrong, generative adversarial network. And later people have used that dataset for many other examples. Okay. Similarly, MNIST dataset, all of you know about MNIST dataset. It's the handwritten dataset where you have handwritten 0, 1, 2, 9. So if you, and there is around 60,000 to 70,000 images. So what will happen if you train a generative model on those MNIST dataset? It will learn the distribution over the numbers. And now if you Generate samples, it will generate sometimes 0, sometimes 1, sometimes 9, sometimes 8, sometimes 5, something like that. On the contrary, if you condition on cell 0, then it will generate different handwritten zeros. You understand? So that is the conditional network. Okay.
So if we train the model based on the images of 0, so it's same like
no. Then if you train only based on 0, then you will only generate 0. But the problem is that you had 70,000 data set. And in conditional, you were training from 70,000 data set. But if you take only select the zeros from there, that zeros might be 5,000, which might not be enough to train your generative model, only based on 0. Then you might not have enough data.
which are not 0, will they also contribute?
They will contribute when it is conditional. Otherwise, it will not, because you are only training on 0. So how can they contribute? Yeah, obviously they will, because all the data you are using, right? So there is some sharing of information that is happening. Okay. So that brings us to the end of invertible neural network. And I have 10 minutes, kind of 10, 12 minutes, in which I will start with another model. But before that, any doubt on the invertible neural network part? Remember, invertible neural network is a type of generative model. The next model we will talk about is another type of generative model. Okay. Okay. So there is no question. Let us move ahead. The next generative model that we will be talking about, and the last thing for this course, is denoising diffusion model. Diffusion model. Okay, or we call it DDM. This is the state of the art right now. All the generative models that you see now are mostly based on denoising diffusion model. Although I personally prefer invertible mode, because it can do many things which this one cannot do. But this is the state of the art. Okay. But to this, and by the way, you can think of it as an improvement over VAE, which stands for variational autoencoder. So that's why we will, let us start with VAE slightly, and then we'll draw a parallel with VAE to discuss denoising diffusion model. Okay. So remember, VAE or denoising diffusion model, these are all generative models. Okay. So now, so you want to generate new samples. So in VAE, without going into details, on a surface level, the architecture looks something like this. So this is your input X. Okay. Then you have a network. Okay. And I am drawing the network like this because there is a reason for that. And here you will get Z, which is your Gaussian random variable. You want it to be Gaussian at least. Okay. And then you have a decoder or a network, again neural network, and that will give you X dash. Okay. So think about what is the goal here. What you are trying to do is that you have images, you are trying to convert that image into Gaussian distribution Z. Okay. And then you are trying to reconstruct it into X dash, which should be similar to X. So there are two parts you are trying to do. First, from X you want to go to noise, and from noise now you want to reconstruct. Why do we want to go to noise? Because if you go to noise and if you train your model like this, during inference, prediction or generation of new thing, what will you do? You will ignore the left hand side. Okay. Z is there, which is Gaussian, so you can generate new samples of Z, Gaussian sampling. You will pass it through the right hand side network and that will generate new x. That's why you want your latent variable to be following Gaussian distribution. So when you train, you will train the whole network, but during inference, you will ignore the left hand side and only the right hand side will be of interest. Clear? Clear? Now, what are the two types of loss you will have here? You will have two losses. See, the first loss to train this model will be reconstruction loss. Which means whatever image you are giving during training should match whatever it is generating. So, this is the number one loss, which is the reconstruction. Right? Whatever image you are giving, and it should reconstruct the same thing or similar thing. So, that difference should be minimized. Clear? Second one, what is the second loss? Someone can guess? What is the other constraint that is there on this network? You want your latent variable to be Gaussian. So that means you will force this network output, whatever you get here. This is the output, right? You will force it to be Gaussian. So this will be a Gaussian or KL divergence between Gaussian and whatever you are getting, right? KL divergence loss, which will try to make your these variables Gaussian. Clear? That's why there are two losses. Okay. One more question part. How are you converting your x to z? Through a network. So this part of the network, I will call it 1 or N1. N1 is known as encoder, because it's a neural network, a usual neural network, but it's trying to encode x into z, and you want a specific form of z, right? And it's a network, that is the most important part. Okay. And what is this? This is trying to decode z into x dash. So then you will call it decoder. Clear? So during training, you will have some data x, you will give it to the network x, it will, based on those data, it will try to find out the parameters of n1 and n2 by minimizing two loss. One will be the KL divergence, which will try to make the encoder output to be as Gaussian as possible. The other will be the decoder loss, which will try to match the decoder output with the input you have given. And through these two loss function, your total network gets trained. The loss function is a summation, you don't train it separately, you train it together. Clear? During inference, you let go of n1. So z is now there, you generate z on your own by sampling a Gaussian. And then you pass it through n2, which is decoder, that will generate new x. That is the whole philosophy of VAE in a nutshell. Obviously, mathematics and all those things I am ignoring for now. Okay. Clear? This same philosophy is used in diffusion model. The only thing that diffusion model observed is that there are two changes, actually, major changes. First major change is that, or it's a philosophical thing you can think, that if there is a, let's say, large company, right, and you want to make some serious changes and you want to change the direction of the company, can you do it overnight? No, you will have to make small changes throughout, maybe over 1 year, 6 months, something like that, and that's how the changes happens. It's like a big ship. If you have to change the direction, it moves slowly, right? Same thing was observed here, that it is not fair on N1, the encoder, that you are expecting that one encoder network will directly transform x into z. Much better to do it in steps. That was observation number one. And same observation for N2 also, that when you are trying to generate X from Z, again, it's not fair that there will be one network which will do it, the decoder one. You should again do it in steps. This is the first observation or first change, I will say. The second one is that if I have to convert X to Z, why do I need a network? Can I not do it analytically? Okay, or by doing some mathematical manipulation. And that is what denoising diffusion model does. It does it analytically without any training required. So in denoising diffusion model, X to Z transformation is done analytically without the need for any network, and Z to X is done in steps. Clear? Philosophically, this is the difference between the two. So with that in mind, keep that picture in mind. Now we will discuss the philosophy for 1 minute or 2 minutes. Okay. So denoising diffusion model. The philosophy is simple. You have x0, and from x0 you go to x1, x2, xt. Okay, and this is known as the forward process. Forward process is equivalent to the encoder. Okay, so this is forward process. Which is equivalent to encoder. So if forward process is equivalent to encoder, what is x0? Encoder is n1. So if forward process is equivalent to encoder, then what is x0? The data, the image or whatever, right? This is the data. And what is xt? Z. It is supposed to be equal to z. Right? Clear? The reverse process will be x0, x1, x2, xt. Okay. This is the reverse process, and this is like the decoder. Now for the forward process, what do you need? See, this is a Markov process. So x2 depends on x1, x3 depends on x2. So you will need what is known as the transition density, which is q of xi given xi minus 1. Okay. And this is, I am giving you the formula directly, xi given square root of alpha t xi minus 1 comma square root of 1 minus alpha t I. Okay. Now why this square root of alpha t and all those things is coming? So see, you want to add a Gaussian noise to your data and you want to add it slowly. What will you want at when it reaches steady state? At t tends to infinite. What are you expecting? Or what do you want xt to be? You Gaussian with not just any Gaussian, with unit variance. So it can be proved, and we will prove it next time, that this form of Gaussian ensures that as t tends to infinite, you actually get a unit variance, a standard Gaussian basically. For any other alpha, you will still get a Gaussian, but it will not be having unit variance. So this square root of alpha t and square root of 1 minus alpha t comes from the fact that at the steady state, at t tends to infinite, you will get a standard Gaussian. Clear? And there is nothing to learn there. A parameter which you will decide, but it will hold for any alpha t, but it is between 0 to 1. For the reverse process, that's where neural network will come into picture, because you will try to do it using the reverse process. So here you actually need q of xi minus 1 given xi. This you don't know, so this you will replace with p of theta xi minus 1 given xi. Okay. But this mathematics part, I don't want you to, if you are not able to follow, that's fine. The philosophy you should be able to follow for now. Mathematics we will do Monday. Okay. But the philosophy is simple. You start from a data, keep adding small noise until and unless what is remaining is only noise. So that's the philosophy. You take an image, add noise slowly until and unless it's only noise. And that's the forward process. The reverse process is you take that noisy thing, now denoise it slowly until you can recover the image. Since you are denoising the image, the name is denoising diffusion model. So denoising, the name came from there. Diffusion, because this follows a diffusion model in stochastic differential equation. So that's where the diffusion name comes from. Denoising because you are denoising the process. Okay. So we'll start with this thing and discuss the mathematics. It has some heavy mathematics actually. We'll talk about it on Monday, which hopefully will be the last lecture. One thing we want to discuss before we wrap up is the date for presentation. So there are two options I can think of. One is 28, the other 28th of November. The other one is next Wednesday. Next Wednesday is what, 13th, I think. So before minor, if it has to happen, it has to be on 13th. After minor, I'm also fine, but then it will be 28th. Not before that, because 26th is BTP presentation, 27th is MTP presentation. And before that, 23 is the last exam. So 24, 25, anyways, I will not take anything. So what is the preference? How many for 28? So this Wednesday, everyone? Okay, so before the minor? Okay, so then we will have it coming Wednesday. Okay, so coming Wednesday, we will have our presentation. I'll share the schedule. We'll have it in the same room, 4 LT2. Okay, and you have to submit the presentation also. So I'll create a Moodle link for that. Okay. Okay then. Thank you.